Hello, welcome to this video. This is 5-1 and we are going to talk about the mean value theorem. The mean value theorem, abbreviated as the MVT, is the cousin of the IVT, and we're going to go ahead and compare today the mean value theorem after we introduce it, as well as the intermediate value theorem and how we use them to help us analyze functions. So we're going to go ahead and set the stage, and I'm going to talk about two types of change, which will get us started with the mean value theorem. The two types of changes I'm going to talk about: average rate of change and instantaneous rate of change. Now remember, the average rate of change, this is given a function over an interval, that is the slope of the function over that interval. So to calculate that rate of change, I take those two function values, y2 minus y1, and I subtract x2 minus x1. Now, instantaneous rate of change, given the same function and the same type of interval, instantaneous rate of change is the slope at a specific point. It's the slope at a specific c value. Okay? Well, right here it says find the average rate of change of f of x over the interval 1 to 5. So if I wanted to go ahead and calculate average rate of change, what I need to do is I need to calculate f of 5 and subtract f of 1 and divide by 5 minus 1, right? It's my y values minus my x values, okay? And so I did some math ahead of time. F of 1 was 2. And then f of 5 was 10. So we have 10 minus 2 over 4, which gives us 8 over 4, which is 2. That's the average rate of change over that interval. Now, compare this with a question that says, find the instantaneous rate of change of f of x. Well, again, instantaneous rate of change, that's just the derivative. So f prime of x, this gives us 2x minus 4. And remember, I'm using the function up here at the top of your screen. So x squared minus 4x plus 5. There's my instantaneous rate of change. Okay, next question. Is there a value of x? Is there a value of x where the instantaneous rate of change of f of x equals the average rate of change of f of x over the interval 1, 5? Well, our instantaneous rate of change, f prime of x, that was equal to 2x minus 4. And what we want is we want to know where is the instantaneous rate of change equal to the average rate of change. Now remember, on that interval, our average rate of change, what we just found right here, was 2. So is there a spot where my instantaneous rate of change equals my average rate of change? And now, a couple of ways I can go ahead and solve this. I'll add 4 to both sides, so we get 2x is equal to 6, and thus x is equal to 3. Now we could also look at this visually, and I think this is really, really powerful to help you kind of understand the mean value theorem. The mean value theorem. And it's not called the mean value theorem because it's so mean. Such a mean theorem. No, mean. Remember, mean means average. So this is kind of our foundation, and visually you can see this here. So there's my interval 1 to 5. There's my average rate of change in the blue. And then notice the instantaneous rate of change is also 2 at 3, at x equals 3. Okay, so where are you going with this, Schwarber? In the example above, we were able to find a value in the given interval. That's important, in the given interval, where a rock is equal to I rock. It is natural to wonder if this is always the case. Can we always find a place where f prime of x equals the average rate of change of f of x in a given interval? This is the basis for the mean value theorem, abbreviated MVT. Now, whenever you use the acronyms, I like you to actually use the words mean value theorem and to write them out: mean value theorem, intermediate value theorem, because MVT and IVT are so easy to switch. You kind of almost do it subconsciously. You can switch them, and then you'll lose that point, or at least the justification point, and we don't want that. So, continuing on, the mean value theorem is an existence theorem. existence theorem. Just like the intermediate value theorem, it's an existence theorem, if you can read my writing. This type of theorem is important in mathematics because they guarantee that a value exists. That's why they call them an existence. You're guaranteeing something exists. Okay, and we've already seen one, the IVT. All right, so let's go ahead and let's kind of look at this idea and see if we can start to kind of generate the MVT. What is the MVT? So they say here for example number 1, for each of the functions below, draw the segment between the indicated points on the graph. Is there a point on the graph between the indicated points where the slope of the line tangent to the point is equal to the slope between the two given points? If so, sketch the tangent line. All right, so let's go ahead and look at the first function here, f of x. And I have my two indicated points. I want to go ahead and I want to draw a line between these 2 points. Now, if you have a utensil such as a ruler or maybe a card from your ID card from your wallet, that can be used as a straight edge to help you kind of just generate a quick straight line. You can go ahead and use that. So I'm going to go ahead, I'm going to use my ruler to generate a line, slope between these 2 points. Ta-da! There is my line segment. So I just created a straight line between those 2 points. Now, what I want to go ahead and do, is there a spot on this graph, the tangent line? Remember, that just touches the graph at one point to where it has that same slope, that would have that same slope. Well, none of these are all like negative slopes. And as I come down here, it's 0. We're starting to get in the right direction. And then here, these lines are going to be super, super steep. But maybe right here at 5, if I'm at 5, that tangent line, remember, it's going to touch at 1 point. That would give us a similar slope. Let's see if I can draw this. It's not letting me draw. Here we go. Right there. Okay. So there's a point where we do have it. Yes. I'm going to put a big yes right there. Okay. Let's go ahead and look at this example. Well, in this example, if I go ahead and I connect these 2 points here. There we go. I'm looking for a slope of a line tangent where the instantaneous rate of change, because that's what it is equal to this average rate of change between these 2 points. Is there one? Well, this is a straight line, so I'm not going to have any points on a tangent line here, because that would just be the entire line. So in this case, no, I don't. I do not have it. Nope. There's not one there. Okay, let's go ahead and look at example number 3, h of x. Okay, here for h of x, I can go ahead and create this line. All right, ta-da! There is my what's called a secant line, my average rate of change line between those 2 points on the interval. And now I want, is there a point on the graph where the instantaneous rate of change is equal to this? So imagine a straight line. If I had a straight line at this point, no, that's not kind of equal to it. Here, no, getting closer, but you can kind of already see I made a point at 5 where the instantaneous rate of change is equal to this. So here's my tangent line. Okay, and notice that that's equal to that instantaneous rate of change. So yes, it is. Okay, last example here. Is there a point where the instantaneous rate of change is equal to the average rate of change on this interval? And I'll go ahead and draw this straight line. So is there a point? Well, this is going to go like this. Maybe right here at 4. At 4, that's kind of close. But then I jump up here, and then all of a sudden these slopes are negative. So at this point, for this example, no. I do not have a point where the slope of the tangent line would be equal to the to the average rate of change. Okay. So, in the examples above, which graphs were you able to find a point between the indicated points where the instantaneous rate of change is equal to the average rate of change? And under which circumstances do you think we can guarantee a point if the instantaneous rate of change is equal to the average rate of change? Well, we were able to create these two instances for f of x and h of x, okay? We are not able to find them for g of x and k of x. Now, what's the difference between these two functions? Well, I can tell you right away, k of x is not continuous. K is not continuous. And then what's wrong with g of x? Well, this one's not smooth, or more so, g is not differentiable. It is not differentiable at every single point, meaning I can't take the derivative right here at these sharp turns or cusps. Okay, so that has something to do with it. Okay, well, let's go ahead and meet the mean value theorem. So that's just some kind of background work generating our idea around the mean value theorem. So here's the mean value theorem. They say if f is continuous on the closed interval a to b and it is differentiable on the open interval a to b, then there exists a number c in a to b such that, and this is the very, very simple part, I rock is equal to a rock. Okay, so we're going to show that average rate of change is equal to instantaneous rate of change, or more so, use this idea, right, to prove that the instantaneous rate of change as some value exists. Okay, so what are the big ideas of the mean value theorem? Number one, the function must be, like we said, continuous on the closed interval and differentiable on the open interval. Those are your two conditions. Those are your two conditions that we're going to go ahead and show. Number two, the NVT guarantees that I rock is equal to a rock somewhere in the interval. Somewhere. Doesn't say exactly where, but somewhere in that interval, right? And that interval being a comma b. MVT is an existent theorem. It guarantees something will occur, but it doesn't specify where. I kind of already talked about that. And then number four, we will approach MVT problems in a similar way we did IVT. Check the conditions, use the endpoints, and then state our conclusion. Okay? All right. Let's go ahead and let's look at some examples, and let's just check and see, okay, am I going to go ahead and apply the IVT or the MVT, and then verify the conditions if they are appropriate. We do not apply them in these next two examples. Okay, example 2. For the following problems, read the information given and determine which existence theorem, the IVT or the NVT, is appropriate. Then verify the conditions to see if the appropriate theorem can be applied. Do not apply the theorem. The function f is continuous for all values of x. Selected values of f of x are given in the table above. A. Is there a time c, 1 is less than c, which is less than 7, such that f of c is equal to 2? Well, this is specifically asking about function values. It's not asking about derivatives. This is an intermediate value theorem problem. So, can it be applied? Well, condition number 1. They say f is continuous. That's good. Condition number 2. We want our k value, -2. We want f of c to equal -2 is between our function values f of 1, which is 8, and f of 7, which is -4. And is it between? Yes! There we go. Yes, we can apply it. B, is there a time r, 1 is less than c, which is less than 7, such that f prime of r is equal to -2? Give a reason for your answer. So here they're asking for the instantaneous rate of change about f. Okay, well, this is going to be the mean value theorem. The mean value theorem. So, because they're asking about instantaneous rate of change. So, can it be applied? Well, number one, is it continuous? Yes, f is continuous. Okay, and it's specifically on the closed interval. The closed interval 1 to 7. They tell us all values, it's continuous. Okay, condition number 2. Is it differentiable on the open interval? Is it differentiable on the open interval? Well, they don't tell us at all that if the function is differentiable. So therefore, it's unknown. I'm going to say unknown if f is differentiable on 1 to 7. No, cannot apply the MVT. We do not know. We have to know. All right, example number 2. For t is greater than 0, the velocity of a particle moving along a straight line can be modeled by the differentiable function v. Okay, differentiable function v. Selected values of v of t are given in the table above. Okay, must there be a time k, 2 is less than k, which is less than 11, such that a of k is equal to -1? Okay, well, what am I going to, which theorem am I going to use? IVT or MVT? They're asking me, must there be a time? So I'm going to go ahead and I'm going to use the MVT here. And the reason is because I'm given information about velocity, and now they're asking me about acceleration, the derivative of that, the instantaneous rate of change of velocity. So this is the MVT. So I'm going to go through my conditions. Number 1, is f continuous? Well, since, I should say v rather, since v is differentiable, it is continuous. Number 2, v is differentiable. Okay, so there you have it. If it's differentiable, it is continuous. So answer here is yes. We could go ahead and apply the MVT. Okay, and I know I didn't give specific values, but they say for all t greater than 0. So for all t values there. Okay, before we go ahead and dive into some actual real AP level problems, what we're going to do is we're going to kind of recap and contrast and compare the IVT with the MVT. So really quickly, let's go back over the conditions. The conditions for the IVT, number 1 is it must be continuous. F is continuous. Okay. Number 2, f of c equals k must be between f of a and f of b. Okay, so those are your 2 conditions. Your conditions for the mean value theorem, number 1, f is continuous. F is continuous. And I'm going to put here on the closed interval a comma b. And then number 2, f is differentiable. You're dealing with instantaneous rate of change, so that's how you're going to kind of delineate between these 2. You need differentiability for when you're taking and working with the derivative. Differentiable. And this one is on the open interval, a comma b. Okay, so what do we go ahead and look for? How do I know when to use this? Well, you're going to look for a conclusion about function values, shown in the table, but missing. So like on that last problem, they gave us velocity. If they said, is there a time where velocity is this? They don't show you that, but they give you information about velocity. You're just trying to pin it between certain values, kind of like right here, right? So if they said, is there a time when the velocity is 3? Maybe right between 0 and 1. Okay. However, for the mean value theorem, you're going to look for, they're asking for a conclusion about the rate of change of the function shown in the table. Okay, and I'll go ahead and I'll kind of highlight this here in these next two examples. Okay, so remember, this is the IVT side. A bug is moving along the x-axis. The bug's velocity is differentiable and selected values are given in the table above. Is there a time c for 0 is less than c, which is less than 9, such that v of c is equal to -1? Give a reason. Well, notice here, I'm given velocity. So that means I'm looking for a time when the velocity is -1 in between these function values. That's an intermediate value theorem. You're trying to peg a value in between, right? Other values. Okay, how about here? Well, for this one, they say all of the same things, except they say such that a of c is equal to -1. Well, that's acceleration. Again, this is velocity, so I need the derivative. They're asking me about the derivative of this function. That's the mean value theorem. Okay? All right. So how would we go ahead and show this? Well, for the IVT, number 1, you need to state continuity. Okay? So V is differentiable. And then therefore continuous. Number 2, v of c is equal to -1, again, which is between, and then here's where we use our endpoints, right? So v of 0, which is 5, and v of 9, which is equal to -4. So it's between those two values. There you go. There is your work. Okay. Over here, so v is differentiable, and therefore continuous. That's nice, because they kind of give you everything, right? And then what we're going to go ahead and do is we need to calculate, okay, what is v of 9 minus v of 0 over 9 minus 0, the average rate of change on that interval, okay, which happens to be -4 minus 5. We just found those values, divided by 9. So we have -9 over 9, which equals -1. Okay, and thus we have shown, right, a of c is equal to v prime of c, which equals -1. So there's the work, right? In this one, intermediate value theorem, you just had to show that this value is in between. Here you have to show average rate of change is equal to instantaneous rate of change, right? That's what they wanted you to show. And then here's our statement conclusions. Since v of t is continuous on 0 to 9, the IVT, the IVT, that was supposed to go here, guarantees that there is a time c for 0 is less than c, which is less than 9, such that v of c is equal to 1, -1. Okay, and then for the mean value theorem, since v of t is differentiable on 0 to 9 and continuous on 0 to 9, the MVT, the mean value theorem, guarantees that, again, you're just going to copy what the sentence asks, or whatever the question's asking you, that there is a time C for 0 less than C less than 9 such that A of C, which is the same thing as V prime of C, is equal to -1. Okay? Okay, that's going to do it for this portion of the video. That was really an introduction into the MVT and contrasting it with the IVT. We're going to go ahead and dive into examples that you'll see on the AP test in the next video. Give me a thumbs up, like, subscribe, catch you in the next one. See ya.